Chapter 7 introduced a method to calculate shear force as a function, internal shear force as a function of location, and also introduced the same method to calculate the bending moment, internal bending moment, as a function of location. So after we got those two functions, then we need to plot. And such diagrams are called the shear and moment diagram. So we are basically following some kind of procedures. As a first step, we try to calculate the reactions with a given beam problem, because for any beams, you must have the supports, right? So then, obviously, we do need to calculate the reactions as a first step. And after we're done with the first step, we need to see for each given problem how many what's the minimum number of cut we have to do. I'm talking about the minimum number. If you cut more, there's nothing wrong. But of course, it's going to be some kind of time involved. So that's why I keep talking about the minimum number of cuts we have to do. And after we identify those minimum number of cuts, then in each segment, we need to build up those two important equations, allowing us to calculate the shear force and the bending moment as a function of the locations. And finally, we're going to plot those two functions. And that's supposed to be ended for that given problem. So today, I'm going to continue to talk about the second example. So we talked about the first example last time. We finished up the first example with concentrated load acting on the certain locations. For this problem, obviously, the minimum number of cuts need to be 3. Somewhere here as a first cut, somewhere here a second cut, and somewhere here the third cut. So after we're done with those cuts, obviously, we can finally plot the shear and the bending moment diagram. These shear and the bending moments are all internal forces. In other words, if you do not cut, you are not going to see those. Okay, so that's why when you look at the original free body diagram for the entire structure, we do not see, in fact, internal shear force or internal bending moment anywhere, because they are inside. So in order to let them show up, you have to cut. And that's why we need to identify the minimum number of cuts. Okay, so today I'm going to talk about the second example. I introduced this example briefly last week, but I did not finish. So today I'm going to give you all the detailed procedures to show how we're going to solve this kind of problem. And this problem is pretty much similar, except this time we are dealing with the distributed load this time. So previous example, we are only having the concentrated load. So for a typically concentrated load, the shear force distribution are pretty much piecewise constant. Correspondingly, the bending moments are pretty much piecewise linear function. However, for uniform distributed load, typically the bending moments diagram is supposed to be quadratic at some locations, a certain range. And then the shear force can be linear function. Okay? So let's talk about this one more carefully. Our final goal is to plot the shear diagram and the bending moment diagram for the beam AB given above here, this beam AB. The distributed load, the uniform distributed load, is having intensity of 40 pounds per inch. So that's a 40 pounds per inch, extending from 0 all the way to point C, which means 12 inch from A to C. In addition, there is a 400 pound load applied at the point E. So there's another force acting on here, which is not directly here. So in other words, this part, DE part, is not the part of beam. The beam, we still talk about ACDB. However, it's just kind of like a attachment here. There is additional force acting here. In other words, somehow we have to move this force back to this point, point D. And that is the technology we frequently use in Chapter 3, which I'm going to show you. But no matter what, for this kind of beam problem, as a first step, we need to calculate the reactions. In other words, we're always having some kind of supports. Then by looking at the entire structure, we can calculate the reactions at the first step. After we're done, then we are going to determine what's the minimum number of cuts we have to do for this problem. And then in each segment, we just need to calculate the internal shear and the internal bending moment. And finally, we're going to summarize the solutions we got and the plot in terms of these two diagrams. So that's a typical procedure. So now I'm switching back to the overhead projector just to show you how we can solve this problem step by step. Okay, smaller. As I said, the first step, number one, we need to plot the free body diagram for the entire beam or entire structure. Okay, so then what we're going to do is to identify the rigid body, which is this. This is the point A, and this is the point B. Here is a point C, and this is a point D, and we have a force acting on point E with a magnitude 400 pounds. In addition, we have uniform distributed load acting between A and C. Okay, so this is the rigid body with applied forces applied on it. Point A is a roller, so we cut here to separate the rigid body from the support. Then correspondingly, we need to give a reaction. Let's call RA. At the point B is a pin support, so when we cut this one, then correspondingly we need to give two reactions. Let's call RBY, RBX. Okay? So with this given free body diagram, we should be able to write down three equilibrium equations. So first of all, we always try to collect all the forces in x direction and set equal to 0. So then immediately we find out Bx equal to 0. Okay? I think there's some questions somebody asked before regarding this so-called Bx equals 0. You say, oh, if always Bx equals 0, why do we need to use a pin to support at one end instead of using a roller? Because you don't need this Bx. Bx equals 0 for all the forces going to the vertical direction. There's no any force in x direction. Why do we need to use a pin? Instead, can we just use the two rollers? If you use two rollers, ideally that's the same problem. However, such design does not provide with any disturbance. Just in case you have very tiny horizontal force acting on the real beam, then there's no reaction, there's no resistance. So that's why typically you have to have at least pin to make sure the structure is stable, even though frequently this Bx equals 0. Okay, so from the first equation you get Bx equals 0, leave it there. Now the second equation, typically we are collecting forces in y direction. So then we are saying RA going up plus RBY going up, and then you have a 400 pounds force going down. Okay. And then there are forces which are distributed applying between A and C. So how are we going to consider the contribution from distributed load in this equation? So I hope you still remember there's some kind of things in chapter 5 we are making the equivalence. In other words, this distributed load is equivalent to a concentrated load acting on the local center between A and C. However, if I'm asking you, originally from this structure, in reality we have distributed load, 40 pounds per inch, starting from point A all the way to point C. Is this one the same with a concentrated load acting on the local center between A and C? The answer is no, they're not the same. But in order for us to calculate the overall reactions, we use such equivalence. Such equivalence can let us calculate the reactions and somewhere a little bit far away from that location. But obviously, a concentrated load acting on here versus a distributed load acting on from A to C are two different concepts. They are similar, but in fact they are not identical. Here we call this is equivalent is because we want to calculate those reactions. So in other words, we always make the equivalence after we plot the free body diagram, and that's a very important concept. So later on, this is the first step. Later on, when I move to other step, I'm gonna reiterate or emphasize why we need to do this kind of equivalence only after we plot the free body diagram. So in other words, you are now supposed to make the equivalence between the uniform distributed load and the concentrated load on the original structure because they are now the same thing. The reason we have to do this is because we don't know how to calculate, how to collect the y direction force if they are uniform distributed load. We don't know how to do it. We only know if they are concentrated load. So that's why we want to transfer this uniform distributed load to a virtual concentrated load. But this only occurs if you already plot the free body diagram. Okay? Now, once we understand this concept, we say, okay, distributed load is equivalent to this one. Then what is the magnitude of this virtual concentrated load? What's the magnitude? The magnitude equal to this whole area. Or in other words, you use a 40 pounds multiply the whole span from A to C, which is 12. So 40 pounds times 12, that gave you this kind of area. And that area is the total force, equivalent to the concentrated load as their magnitude. So this should be going down as well. That's why we put the negative sign here. And then finally, that's equal to 0. Okay, so keep in mind, you can only do the equivalence after you plot the free body diagram. So don't say this one in the original structure, you say that's equivalent to a concentrated load. In principle, that's not true. Okay, so that's the equation having two forces involved. There's nothing we can do. We just leave that equation there. So we're going to come back to use that equation. So now we need to collect a moment equation. How are we going to collect the moment equation? We need to find a point and to calculate the moment of that point based on all the forces. Okay, so which point we want to choose? We can choose any point we like. Let's say we choose point A. So let's say we choose point A. Now we are going to calculate the moment due to all forces. So number one, we have the equivalent concentrated load acting at a center between A and C, and the magnitude is 40 times 12. So this together is the magnitude of this concentrated load. Then this magnitude need to multiply with the shorter distance. So the shorter distance is from the point you want to calculate the moment to the force line. So this is the force line, then from here to here. That should be half AC. So AC is 12 inch, so half divided by 2. And this force should have the potential to rotate the whole structure at point A clockwise. So then you put a negative sign here. So this is the first term to identify the moment of this virtual concentrated load at point A. Any questions? Yes?
How come you chose point A instead of point B? Like, is there any...
Yes, well, the last time I was choosing point B, so this time I just want to change a little bit. It doesn't really matter. Okay, yeah, we finally end up with the same answer. If you already wrote down something, you don't have to write here. Similar, very similar, okay? But I just want to use a different way, in fact. Okay, just in case some student would like to choose another point. So any point you finally end up with one equation, allowing you to calculate one unknown. And then you bring that result you got back to the second equation to calculate another one. Okay? Any other questions? Okay, so this is the moment due to the virtual concentrated load, but there are other forces, right? You have RA, but we're not going to consider RA. It's because RA is going through point A, so equals 0. So the moment of RA equal to 0. Okay, so forget about this one. Now we have a force acting on point E, and the magnitude is 400. So this is the magnitude of this 400 force acting on point E. Now we need to multiply with the shorter distance. That's called D. So what is the D? The shorter distance. From this point A, you want to calculate the moment to the force line. So this is the force line. So then the shorter distance should be this. So that means from A to E. So A to E from this picture is going to be 10, 22, right? Okay, so altogether that is the moment. Now we need to determine the direction. So this force is going down, so it has a potential to rotate along at this point A clockwise, so that's negative sign as well. Okay, now finally we have another two forces, but RBX is going through point A, or by taking advantage of this one anyway, so I forgot, it's RBX, not BX. RBX, okay? So that's equal to 0 anyway, so that's fine. So we don't need to worry about that. Now we have RBY. RBY, which is the force acting on point B, and the magnitude is RBY, and it's going up. So then that's going to potentially rotate clockwise, counterclockwise, that's positive. Now what's the shorter distance? From A to B. From A to B is 32. Okay, then that's it. Let's go 0. Okay, so from this third equation, there's only one unknown involved, which is called RBY. So immediately from this third equation, you get RBY equal to something. So let me just write down the answer for you. So RBY equal to 365. And the default unit is pound. And we got a positive, so that means the assumption we made having RBY going up is correct, because we finally got a positive 365. Okay, so now with this result, we are plugging RBY, which is equal to 365, back into the second equation. This one, because this one we still have RA undetermined. So then from this one, we get RA equal to 515. Okay, and also going up because we got a positive. So it really doesn't matter whether you choose point A, point B to calculate the moment equation. And you can combine both so that you don't have to use the second equation. So the bottom line is, for any given free body diagram for beam problem, or in general for any two-dimensional rigid body problem, you should write down 3 equations in general. You can write more, but the independent number is 3. So you can write 10 equations, you pick 10 points, you can write 10 equations. It will not help you to solve for 10 unknowns. You can only solve for up to 3 unknowns, okay? Because only those 3 equations are independent from each other. So that's the first step. We have got all the reactions. Any questions? Now let's move to the second step. So starting from the second step, first of all, we need to determine what's the minimum number of cut we have to deal with. Okay? So back to this picture we have here. So obviously we're going to try to assume we are traveling from point A all the way to point B. Okay? So to determine what's the minimum number of cuts, so we keep walking slowly from point A to the right. Every time when we move more, there are additional more forces, because this is a distributed load. Okay, so they're distributed load. However, these distributed loads are not discontinuous, because keep adding very, very small amount. So it's still continuous. Okay, so that's why we just keep moving until we see point C. We have to stop at point C, because at point C, all of a sudden, the force increase, or stop maintaining with a constant uniform distributed load. So then obviously this should be our first segment. So in other words, we need to have our first cut somewhere between A and C. Make the first cut. We don't need to have a more like 2 or 3 more 5 cut. We don't need. On the other hand, you may say, well, can I first make this uniform distributed load equivalent to a concentrated load acting on the center? If this is the case, if we are having a concentrated on the center, then we need to say from A to this point, we need to make one cut. From this point to this point, we need to make another cut. The answer is no, because again, I'm telling you, when you see the original real structure with whatever force apply, you cannot make such equivalence first. You have to make the equivalence after you plot or you draw the free body diagram. And this, again, is not a free body diagram. This is a real structure with the pin and the roller support. This is not called the free body diagram. And this is the free body diagram, right? So that's why you should not use a virtual concentrator acting on here and then determine, okay, I need to cut somewhere between A to this point. And then I need to make another cut between this point and C. That's totally wrong, okay? Because in reality, if you have a concentrated load acting on here versus a uniform distributed load acting on here, they are two different concepts. The reason we make the equivalence after we plot the free body diagram is for us to calculate the reactions. It's for us to calculate internal, the internal shear and the internal bending moment. Okay? So now we decide somewhere between A and C, we just need to make one cut. We leave it there. We're going to continue. We need to first determine how many cuts we have, right? So from C, we're going to continue to travel to the right. Let's look at, we don't have anything. However, you don't want to go this way because this is not part of B. So we're going to continue to this way. Now, you have to move this force because we're not going through this. We have to move this force back to point D. So if we move this force back to point D, then obviously there is a discontinuity. And specifically, I can move first to determine how many cuts we have to make. How to move a force from one point to another one? Well, we learned that in chapter 3. So in chapter 3, if we want to move one force from point E to point D, for example, how are we going to do that? We are adding two virtual forces at this point D you want to move to. Okay, we're adding two virtual forces. They are having the same magnitude with the force you want to move. That means 400 pounds. But at this point, we have a 400 pounds up, we have 400 pounds down. Of course, that's equivalent to nothing because they are canceling anyway at the same point in the opposite direction. Now, if you look at this one of this virtual force compared with the real force acting on point E, so these two forces form a couple, okay? Because they are satisfying exactly the requirement for this definition of couple. Having the same magnitude, 400 pounds, parallel, but in the opposite direction. So that's why these two form a couple. If these two form a couple, then what? Then I'm going to erase these two forces. I'm going to erase these two forces, and instead, I'm going to add a couple. And in other words, add a moment. So now, this one should have a clockwise couple, or clockwise moment at this point. So now, this moment should be 400 times the short distance from here to here, or from here to here. That means 4 inches. Okay? So, finally, we end up with a force acting on point D, which is basically the same with this force. That's why I'm successfully moving that 400 pounds force from point D to from point E to point D with the same magnitude. But in addition, you need to add a couple to compensate such movement. So now, from this point, you clearly see there's a force discontinuity. And in addition, there's another discontinuity in terms of the moment. But at least there's a force discontinuity. If that's the case, now we say when we travel from point C all the way to the right, we have to stop here. So in other words, between C and D, we need to make another cut. Yes?
Is it not the same to just directly move the force at point E up?
I'm sorry, say it again?
Is it not the same to directly move the force at point E straight up to the main bar?
Well, if you move that, you can move that, but that's not quite right, because when you move the force, you have to go through the rigid body, so that if you want to go through the rigid body, that means this one has to go here. Because the reason, in general, you don't need to move, but this is not part of the beam. So that, in other words, we're not going to plot the free body diagram. We're not going to plot the shear and moment diagram on this part. So that's why we need to move this force to a certain point with a part of the beam. But you are saying, can I move to point E to somehow this point? Well, in principle, you can do that. It's not a problem. But it will not help us to plot the shear and moment diagrams. Because in reality, this force is directly applying here through this kind of bridge. And that's why you need to choose that point instead of choosing point E. Or in other words, I can say, well, can I move this point E, the force in here to some other point? That's not quite correct if you are plotting the shear and the moment diagrams. So you need to find a point which is directly connected with this one so that later on you're going to ignore this part because this is not part of the beam. Okay? Yes?
It would be the same in terms of like a force.
No, they're different.
So would it be the same in terms of general forces in general neighborhood, or would it be the same in terms of shear?
Well, if you are moving this force to here to calculate these two reactions, they are the same. But we're not doing that. We're calculating the internal shear and the internal moment at everywhere in the beam. So that's different. So in other words, if you're moving this one to here, then you are not calculating the shear force and the bending moment at this point correctly. But if you want to move this one to somewhere here, and then you're going to calculate those two reactions, they are the same. So if you ever see this kind of additional bridge so that you can easily add a force, then you need to move this one to a certain point directly connecting to the to this point E. And that's the point, that's point D. Any other questions? Yes?
So, in calculating where to break, when you start from A, why don't you break immediately after passing A? Because you have the force coming from the pin, and you have the force from the distributed load, and after you pass the pin, there's no more force below you. So, you're going to change right there.
Wait, I'm sorry, say it again. You're saying.
So, right after you pass the pin, like, as soon as you pass the pin, doesn't the force change?
You mean here?
Right.
Yes, the force changed, but it's changed in a continuous way. So in other words, if you call this a point H, and then if you move very tiny to the right, point from H to G, for example, so the increment of force is very, very tiny. So it's not called discontinuous. It's continuous. But the force is increasing, but it's not discontinuous. Discontinuous, there's a jump. It's a finite number of jump. That's called discontinuous. So that's why you don't need to keep cutting. My conclusion is from A to C, you only need to make one cut instead of multiple cuts.
Because isn't there like a resultant force at A? So at point A, there's like some force. And
Yes, point A is the force which we calculated, which is called the 515, right? Yes.
So isn't that technically a discontinuity?
No, it doesn't matter. It's discontinuous, that's fine. But you don't have any material on the left. So that's why we don't need to cut. So if let's say if I have a support at this point, if I move the support from A, from this end to here, for example, okay? If there's real support, yes, you need to separate because there's a discontinuity in terms of force. But this point is at the end already. We are standing at this point and try to move to the right. So then you don't need to say, I'm going to cut exactly point A. A is already cut. That's the edge. So that's why you don't need to cut. If this one is not supported here, it's supported here, for example, yes. From this point to this point, you need to make a cut first. And then from this point to here, you need to make another cut. That's right. But this is already at the edge. You don't need to cut on the left. You only need to cut on the right.
So there's one cut from A to C?
Yes, one cut from A to C. That's a minimum number. Of course, if you're cutting more, it's not a problem. But I'm talking about the minimum number of cuts in order to solve this problem. Any other questions? Okay, so we determined we are moving from C to this direction at point D. We have to stop because now we have a force acting on point D. That is called a discontinuity. So there's a second cut somewhere between C and D. I have to make a cut. And then we keep moving. We're now going to this way because this is no end to the right. So we're moving from D and keep going. There's no discontinuity until we see point B. And that's another cut. So for this problem, we finally end up with the three cuts, right? Somewhere here, and then C to D, and then D to B. So in order to solve this problem, the minimum number of cuts is 3. Any questions? Okay, so once we determine we need to cut 3 times, then we need to add a few more steps, right? Starting from step number 2, we need to make the first cut. So we talk about the segment between A and C. So segment between A and C. So now I'm going to make a general cut, typical cut between A and C. So I'm going to make this cut, and then the structure is split into 2 parts. And now we need to look at one part. So I look at the left side, because left side has less force involved. Okay? So when I make the cut here, I'm going to plot the free body diagram of the part of the cut structure. So this is still point A, but this is called the cutting point. Okay, I cut it here. Now, look at the structure on the left. At point A, I have a reaction because point A is a pin, is a roller. The reaction is 515. Okay, at point A. And between A to this cutting point, I have a distributed load. So this distributed load is now the whole load from A to C. It's part of that because I cut it. So the distributed load will be split into somewhere left side, somewhere right side. I only look at the somewhere on the left side. So now I need to identify the location of this cutting point. The cutting point can be 0.1 inch, 0.2 inch, all the way to 1.2 inch. But I want to make it typical. That means I need to call this X. Because X can be anything from 0 to 12 inch. Okay? So that's why that's called the minimum number of cuts. I use one cut to be equivalent to all the cuts between A and C. As long as I make X movable from 0 to 12 inch. Once I have this cut, typically we need to give 2 reactions, right? One is two shear forces, shear force V, and then the bending moment M. Okay, so this is a new free body diagram. Now we are making the equivalence between the distributed load and the concentrated load now. So that's why every time we can make the equivalent concentrated load to replace the uniform distributed load. So this virtual constant concentrated load is acting on the local half center. So that means half X. Any questions? Okay, so again, after you plot your free body diagram, you can make the equivalence between the uniformly distributed load and the virtual concentrated load. You may say, why do I need to do that? Well, all the Newton's equations are based on concentrated load. So that's why if you want to later write down those 2 Newton's equations or 3 Newton's equations, you need to make such equivalence, the equivalent between the uniform distributed load and the concentrated load. But again, this should not happen in the first place when you talk about the entire structure before you make the cut. So that's why you have to make the cut, you plot the free body diagram, then you are ready to switch, to transfer from uniform distributed load to the equivalent concentrated load. Okay? From this free body diagram, first of all, I'm going to collect all the forces in y direction and set equal 0. Okay? So I'm collecting, there's a force 515 going up, and then I have a shear going down, that's called V. And then I have this virtual concentrated load due to uniform distributed load. So what is the magnitude of this virtual concentrated load due to uniform distributed load? That's going to be the intensity, which is still 40 pounds per inch. So 40 pounds per inch multiplied with the span with the uniform distributed load. In other words, the area. And that is X. Okay? So 40 times X is the magnitude because that's the area. So this should going down as well. That's negative, and that's equal 0. So from this, we can get V equal to 515 minus 40X. So this is a shear force, or the shear force distribution anywhere between A and C. So let me double check. Okay, Any questions? Okay, so this is the first equation helping us to calculate the shear distribution. Now the second equation, which is to take a moment equation at a cutting point and set equals 0 in order for us to calculate the bending moment between A and C. Okay, same thing from this free body diagram. We are collecting the moment due to forces at the cutting point. Number one, we have a force 515. 515 need to multiply with the shorter distance. So from point C, from the point you're cutting to the force line, that's supposed to be x. So 515 times x is the moment due to this force 515, and this is going to be clockwise. So then you put a negative sign in the front. Okay? So this is the moment due to that reaction at point A. Now we have a virtual concentrated load acting on the local center between A and the cutting point. So then what is the moment? First of all, what's the magnitude? The magnitude is a 40x. That's the magnitude. Oh, thank you. So 40x. First of all, this is the moment due to the reaction at point A. Okay, I just reiterate. Now we are talking about the moment due to the virtual concentrated load between A and C, A and the cutting point. So the magnitude of this virtual load is 40x. That's the magnitude of the force. Need to be multiplied with the shorter distance. The shorter distance is from the point you want to calculate the moment to the force line, which is this. So that's a half of x, because that's a local center. Half x. So altogether forms the moment of that force about point C, about point of the cutting point. And this is going to be counterclockwise at that cutting point. And if that's the case, you need to have a positive sign in front of that moment. So keep in mind, this one, you need to see something with x squared involved. And the reason we have x squared because the first x multiplied 40 should be the magnitude of the force. And then you need to multiply the shorter distance. The shorter distance is having x involved as well. So that's the second term, which is the moment due to the virtual concentrated load. Now we have existing internal moment, which is counterclockwise. Then you just add that moment, and that goes 0. The shear does not contribute to this equation because the shear is passing through that point, cutting point. Any questions? Okay, so from this equation, we should be able to calculate m, which is the bending moment. So moment equal to, so we keep this one to the right hand side, take this one to the right hand side, 515x minus 20x squared. Okay, so let me check. Okay, any questions for the calculation of the moment at the cutting point? So these two equations are valid from anywhere between A and C. In other words, x is from 0 all the way to 12 inch, because that's what we call the minimum number of cuts between A and C. We just need to make one cut, which is equivalent to a lot of cuts, in fact, because x can be changed anywhere from 0 to 12 inch. So that's called step number 2. Now we need to move to the next step, step number 3. Step number 3 is to make a cut between between C and D. So again, every time when you try to make another cut, you need to come back to look at the original picture. Okay, to look at the original picture, because the so-called cut is a virtual cut. We're not really cutting the beam. Okay, if you build a bridge and then in order for you to calculate the bending moment or shear force, are you going to cut the real bridge? So that's called virtual cut, just basically to calculate in a virtual way, right? Okay, so step number 3, we are talking about another segment, which is called the segment CD, because we need to virtually cut between C and D. Okay, so let's say from the original picture, we cut it between C and D, then what? The whole structure split into two parts. We just pick one part. Which part we want to pick? Let's say we pick on the left side. So then we pick on the left side, then we are going to plot this new free body diagram. So again, from point A and somewhere going through point C, and this is the cutting point. Okay, between C and D. So at point A, there is a reaction. It's called phi 15. And then between A and C, there is a uniform distributed load. So don't make the equivalence first, okay? You need to originally plot the real uniform distributed load first. And then we're going to do the equivalent after we finish the free body diagram. So here is the uniform distributed load. Now, at this point, we make the cut. There is a force, it's called V, and there is a moment we call M, because the cutting point. After you cut, those two internal forces show up. Okay? So this is another free body diagram. So once we plot this free body diagram, then we can make the equivalence. Say, okay, so this uniform distributed load is equivalent to a concentrated load at the local center between A and C. You may say, why do we need to make the equivalent load? Are we just looking at the uniform distributed load? Well, that's fine, but the question is, later on when you write down the Newton's equations only allow you to put the concentrated load in instead of the uniform distributed load. So that's why now we have to do the equivalence. Okay, so this one is located at the local center between A and C. So A and C together is 12 inch. So then from A to this local center should be 6 inch. Okay, because half. And the magnitude of this force is the area, or in other words, it should be 40 times 12. That's the magnitude of this virtual concentrated load. Okay, so now we are ready to first collect forces in y direction in order to calculate the shear force, internal shear force, right? Okay, so we have a phi 15 going up, and we have 40 times 12, that's a virtual concentrated load going down. And then we have the shear force going down, and that's equal 0. From this, V equal to phi 15 minus 40 times 12. What's the number of this one? 35 pounds. Okay, so this is the shear force. We calculated based on the first equation. The second equation is to collect the moment equation at the cutting point and set equals 0. Okay, so we just look at one by one. First of all, you have a phi 15. Oh, I forgot to say, from here to here is still called x. I already explained to you several times, right, why it's called x. This x is different from the previous x in step number 2. Because this x, the domain of this x is from 12 inch to 18 inch. So it's no longer from 0 to 12. In other words, if you keep moving to the left, the minimum x is 12. So that's why this x is different from the previous x, even though we just happen to call we use the same symbol, which is called x, but the x itself is a variable. Okay, so phi 15 times the shorter distance, which is called x, because from A to this cutting point is x. So this is the moment. It is clockwise, so it's negative. So this totally is the clockwise moment due to a force at point A, which is phi 15. And together is a moment at cutting point. Now we have another virtual force. The virtual force is 40 times 12. Altogether is the magnitude of that virtual force, which need to be multiplied with the the short distance. That's from the cutting point to the force line here. So what is this? The total is x. And from here to the right, to the left is 6 inch. So then this short distance should be x minus 6. So x is the total minus from A to this point. This is the short distance. So it's x minus 6. And this one is counterclockwise. So then it's positive. Okay? And you have a moment plus m equal to 0. So that is the moment equation, allowing us to get the moment. So that should be, put everything to the right hand side, 515 x minus 480 x minus 6. So let's simplify this one. We finally end up with 35x plus 2880. This moment equation. Any questions? Okay. Now let's move to next step. We have one more cut to go. Yes.
Originally, could you have done the same cut, but look at the right side? I remember you saying something like
Yes, we are going to take the right side this time.
But could you
But this one you can do that same thing. Yeah, that's fine. I can quickly do this. Right. So just in case, so since one student was asking, can we look at the right side? Fine. Let's go quickly to the right side. It's the same thing. So I cut it here between C and D, right? So the whole structure here again, I cut in here. So the whole structure is split into two parts. Instead of picking the left side, so just in case, I prefer to take the right hand side. Okay. It just take a little bit longer time. So let's look at the right side. Now we need to plot, so let's say alternatively. Okay, so now I cut it between C and D. I look at the right side. The right side, you are going to have something like this. So this is the point B. You have the reaction. You have an, oh, okay. Okay, so now I look at the right side. This is a cutting point. So now the V is going up, and then there's the moment. This is the cutting point, and somewhere here is called the D, and this is called B. Point B, we have two forces, right? One is a 400 pounds. In addition, there is a moment at this point, which is 400 times 4. Okay, and this one is called the BY, RBY. What is RBY? RBY is 365. So let me put 365 here. Okay, so this is what I call the free body diagram if I pick the right side. However, from this cutting point to the right, you need to make sure you get this identified correctly, because by definition X is always from the cutting point to the left end. That's called X. But now we talk about the right end. So now we need to go back to look at the whole span from A to B. From whole span A to B, 32. It's 32 here. So then this one should be 32 minus X. Okay, so 32 minus X. Now we are collecting all the forces in Y direction. You have V going up, you have 365 going up, you have 400 going down, and that should be equal to 0. Okay, so from this equation, what is V? So V equal to 35, right? Yes, see, this one, and compare with this one, they are the same. Okay, so now let's check the second one by collecting the moment at a cutting point and set equal to 0. Okay? So now let's talk about all the moment, right? So you have a first moment, this one is called M, but it's clockwise, so negative moment. And then you have another moment due to the couple, it's a clockwise as well, negative 400 times 4. And the shear will not contribute, but this one, you have a load acting on point D. It's called point D, right? So 400 times from here to here. From here to here. What's this? So that's going to be the total subtract between D and B. I need to know what's the D and B. D and B is a 14 inch. From here to here is a 14 inch. Given from the original picture. Okay, so now there's a 400 pounds multiply the short distance from here to here. That's going to be 32 minus X total minus 14. Okay, so 32 minus x, that's the total distance from the cutting point to point B, minus 14, because 14 is from this point B to point D. So that's why that's going to be from here to here. And this is going to be clockwise, so that's negative. And finally, you have a 365. So 365 multiplies 32 minus x. That's the moment, but this is going to be counterclockwise. That's positive. And that goes 0. Okay? And let's simplify and to see if this the same thing as, I'm pretty sure it's the same. Otherwise, there's some problem. So let's go. So take moment to the other side. So you have a negative 1600 due to this. And wait. Okay, well, there's a lot of terms. So that's why I don't like to take the right side. So negative 400 times 32 plus 400x plus 400 times 14 is this term altogether. And you have this one plus 365 times 32 minus 365 times x. Oh, sorry. Move up. Now let's simplify further. You have this term and this term together. So 400x minus 365, that's going to be 35x, right? Okay, so now we have this term, this term, this term, and this term, 4 together. You punch your calculator. Let's see what is, well, this one, this one, this one. For those of you who haven't have a calculator, so negative 1600 minus 400 times 32 plus 400 times 14 plus 365 times 32. So tell me the number. I'm pretty sure it's 2880. Otherwise, there must be something wrong. Is that 2880? Okay, good. So see here, we are independently get the same equation with the previous calculation we did by looking at the left side. So through this process, I think you should be convinced, right? It doesn't really matter which, after you make the cut, virtual cut, which side you want to look at, either way. And for this one, it's really hard to say which one is easier, right? It's about comparable, we say this way. Okay, it's comparable, so it's really up to you. But normally, if I were solving this kind of problem, typically, if these two are comparable, I would rather to choose the left side, because the left side, from the cutting point to the left end, that's called x, simple. So if you look at the right side, you have to compromise with something total, subtract x. Okay, as long as you do this correctly, you should end up with the same answer. So any questions with this, what's called alternative calculation? The bottom line is they are the same thing. I just compare, right? Okay, so either way you choose this or choose this, doesn't matter. Now I need to move on to the next step, number 4. So going back to look at this original picture, because every time when you start from a new step, number 4, we need to go back to look at original picture. This original picture. So number 4, we need to look at the segment DB. Okay, so now we need to cut between D and B. So we cut between D and B, then the structure will split into 2 parts. Okay, we'll split into 2 parts. So this time, I would like to choose the right side. You can choose the left side, you compare with the result we have. I'm guaranteeing you get the same thing, but I don't want to look at the left side. There's too many forces now. Okay, so when I cut here, I look at the right side this time. So then I'm going to plot the free body diagram. So this is the point B, and this is called the cutting point. You have V going up, you have a moment going that direction. Okay, and then you have a force at point B, which is, what's the force P? B. B is a 365. Okay, so from here to here, as I said, is a 32 minus x. So this 32 minus x is different from the previous 32 minus x. Again, same thing. Just like we have same symbol x, but the domains are different. Okay, but we still call 32 minus x because the total span is 32. That's why cutting point to the left called x, then cutting point to the right is the total minus x. So 32 minus x. Any questions about the free body diagram? It's simple, just like this. There's not a lot of forces. Okay? Now, by collecting all the forces in y direction, let's see. You have positive y, positive v going up. You have 365 going up, and that's it. Let's go 0. So v equal to negative 365, and it's Newton, right? No, pounds. Okay, simple enough. The second equation, collecting the moment at the cutting point, that's z equals 0. So this one, we have a negative, because it's clockwise, so it's negative moment. And then 365 times the shorter distance, 32 minus x. And this is going to be counterclockwise, that's positive, and equal to 0. So from this equation, we got m equal to, for this one, 365 times 32 minus 365 times x. So let me double check. 365 minus, yes, that's right. Okay, any questions? So this is called step number 4. So now through step 2, number 3, number 4, we got the shear and the moment distributions as a function of x. So now the last step is to plot the shear and the moment diagrams. So we call step number 5. Plot shear and moment diagrams. So again, you need to say x is horizontal direction, and this one you call the v, but you need to plot another one. There's still x, but this one is called m. Okay, and you need to identify the locations. So this is a point A, and this is a point C, that's a point C, and here you have a point D, and all the way to point B and point B. Okay, so now from point A to point C, we need to look at our result, which is here. So step number 2, we got v equal to this, and then moment equal to this. So now let's plot v first. So this time v is a linear function now. As I told you before, if it's a linear function, then you just need to pick 2 points, because that's a straight line. So pick 2 points. So this is anywhere between A and C, then typically you pick point A and point C. So when x equal to point A, that means x equals 0. If x equals 0, what is v? That's a 515. Okay, so first of all, you need to find out somewhere, it's called a 515. And then another point is to have x equal to point C. Point C means x equal to 12 inch. So 40 times 12, that's a 480. So 515 minus 480, that's going to be 35, right? So now you need to pick another point called 35. Try your best to be proportional, but I know there's a big difference between 515 to 35. So now you are plotting something like this. Okay? Because you got one point, got another point, you just connect these 2 points to form a straight line. So that's a shear between A and C. I want to make sure I do it correctly. Let me check. Yes. Okay? So that's a shear. Now we are going to plot the bending moment. The bending moment is this one. But this bending moment is a quadratic function now. So now 2 points are not enough. So we need to have more points. So in order to plot a quadratic function, typically you have 3 points. Okay, or you can somehow pick more points, that's fine. So pick 3 points. So how are I going to pick 3 points? So typically we pick a point at the very end and then pick another point on the very left, right. So very left having x equals 0. So x equals 0, 0, 0. That means you are starting from 0. And then on the very right, that means point C. Point C is to have x equal to 12. So 515 times 12. So 515 times 12 minus 20 times 12 squared. And you have to punch your calculator to get this number. What is number? So, no, 3,300, right? 3,300. You calculate it, but this is what I got from the book. and you do need to write the unit, by the way. So moment in terms of pounds and inch, don't forget, and the shear is pounds. Okay? But don't just simply connect these 2 points. That's not right, because it's a quadratic function. So at least, for example, you pick a middle point having x equal to 6. So when x equal to 6, you plug into this equation, the quadratic equation, you find another number, for example, this one here. So then you can plot something like this. Because it's not straight line. So that's why I don't want you to just connect these 2 points directly. Okay? So that is the first segment based on the solution we got. Any questions? Now let's move to the second one. That is showing here. Let me just show you the result and then we can plot. Okay, so here is the result we got previously from step number 3. The shear this time is a constant, right? The shear is 35. So we got 35, so the constant 35 keep going until point D. Okay, so this is 35. The moment is linear now. That's the moment. If it's linear, we just need to pick 2 points. So first of all, for x equal to 12, and 35 times 12 plus 28 times 80, what's that? I think that's the 3300. So that's still this point. And now you are having x equal to at point D. So x equal to point D, that means 18. So 35 times 18 plus 2880, that's going to be a bigger number. That's the 3510. So 3510. So 3510, you need to make the straight line like this. So this time it's straight line. So that's why we don't need to pick somewhere in between. It's a straight line. Okay? So that's why we plot like this. So that's the C and D. Finally, D and B. D and B, we got the result based on step number 4. So let me just show you step number 4. The result here. So the shear is negative 365. So negative 365 is all the way down to here. That's 365. Okay, so negative 365. So then typically you have to make sure it's continuous like this. So that's a shear because negative 365, right? So we have to make sure it goes down all the way to negative 365. Moment. This is the moment equation, which is linear again. It's a linear equation. So then you need to find 2 points. When x equal to point D, that means x equal to 18. So plug in x equal to 18 and calculate this number. Okay, so this number is not the 3510. Don't assume that. In fact, there's a moment discontinuity at this point. So if you plug in x equal to 18, you punch your calculator, the result is a 5110, in fact. Okay, so it's 5110. That's going up to like this. 5110. And then when you finally put x equal to point B, that means x equal to 32. So x equal to 32 times 365 negative plus 365 plus 30, that's equal to 0, right? So that's finally 0. So in other words, finally, this is the line. Okay? So quadratic, linear, a jump, and another linear function. All together form the bending moment diagram. So let me go back to show you the much better plot from the slides. Yeah, here are the detailed procedure, okay? So basically you will make the cut, whatever, you finally end up with. Oh yes, for those of you who like to look at the final cut between D and B, we cut here, I look at the right side. But actually the textbook show you the details by picking the left side. There's more forces, but you still finally end up with the same result. Okay, so for those who would like to look at left side, you can continue to look at what we have here. But finally, this is the one. So I think they are the same in terms of trend, but again, they are not in scale. In other words, you see here, from here to here is only 35. How come 35 is only 20% of this 515? That's almost impossible, right? But they just want to show you in terms of the variation. Same thing for this one. This is something I really do not like. I think if you were plotting this one, you'd better move this point all the way up somewhere here. Because this point is 3510, and this point is 5110. That's a big jump, in fact. It's not only like this. So this jump is very small. In fact, 35 to 5100, that's a big jump. It should be somewhere here at least, okay? But anyway, so this is a straight line, and then there's a jump. This is a straight line. So this is a very flat, in fact. From 3300 to 3500, that should be very flat. But they just want to show you somehow in terms of the qualitative comparison. And this is not from 0. This is from 0, okay? But I think there's a tiny problem here. This is from 0 because we calculated from 0. So from 0, following the quadratic function to here, linear, and then a big jump, and here. And the reason we have a jump, I told you last time, the reason we have a jump because of this applied moment there, okay? And the reason we have this a force jump because there's real force here. The reason here there's a no jump, there's no discontinuity, okay? It's continuous. It's continuous here. This is, we do not call this a discontinuity. There's no jump. It's because all of a sudden stop, but actually it's a slowly stop. That's why the slope are different, but this is still continuous. But this is the real jump. Okay, so far by looking into these two examples, we can somehow see we can deal with a uniform distributed load to plot the shear and moment diagram. We also have this concentrated load in order for us to plot the shear and moment diagram as well. Okay, so I basically just want to talk about these two examples, but by now you should be able to plot shear and moment diagrams in general chapter 7.